Lesson 15 is called Similarity in Arc Measures in Circles, and before we get started, I highly recommend printing these if you can, just because there's a good amount of vocab on them, and there's some graphics too, so it'll kind of save you some writing. So 15.1, prove circles are similar, starting in the upper left. You can prove circles are similar using similarity transformations such as translations, reflections, rotations, or dilations. And just a quick little review of what each of those means. A translation is something that moves the figure left, right, up, or down without changing the shape or the size or the orientation of the object. I'm going to add in size here because that part is important too. And then the next one, reflection, and mirrors a figure over a line of reflection. Rotation is a circular movement of a figure around a designated point, and then dilation changes the size of an object without changing the shape. So for the next section, we're going to start with this figure on the left, and by the time we get to the right over here, we're going to show that they are similar. If we can take two different objects and apply these like similarity transformations that were listed above and end up with a object that kind of completely overlaps the other one, then we're able to show that it's similar. And similar just means that two different like figures are the same general shape. They could be different sizes, but they're the same general shape. So we're going to start with two circles, circle A and circle B. Circle A is the bigger one on the left, circle B is the smaller one on the right. And then the first thing that we're going to do is if we want to get circle A to overlap circle B, we have to definitely move circle A to the right. So that's going to be a translation. So we're going to translate circle A to the right, and that's what happens in the second picture. So circle A is translated to the right so that point A aligns with point B. And then now you can see there's only this one point here, but it's because they overlap each other. And then now we have circle A on the outside. It's just like bigger than circle B now. So if we need to make something smaller or bigger for that matter, we would use what's called a dilation, where you're changing the size but not the shape. So that's what we're doing in the third picture. We are taking circle A and we're making it smaller with dilation. So circle A is dilated to a smaller size to align with circle B, and then now you can see their center points overlap and they're the same exact size now. So now they're the same exact size and you can see that they overlap each other completely. That means that they're similar. And then that leads us to our theorem, which kind of got snuck in here. Sorry, there's not a lot of spacing there. But the theorem is that all circles are similar. That means that all circles have the same general shape. Okay, so for example 1, list a set of transformations to prove that circle P is similar to circle O. Just a quick little reminder, that little squiggly up there means similar. So circle P is similar to circle O is how that's read, and then in order to show that they're similar, we need to get circle P to align perfectly with circle O to show that they're the same shape, and we would do so with those transformations listed above. So any combination of translation, reflection, rotation, or dilation. So the thing about these problems is there are different like kind of routes that you can take. You may have a set of transformations in your head that could be different than mine, and that doesn't mean they're incorrect. It's just kind of like taking two different roads to the same final destination. So one approach is we could take the same one as we did up above, where we say that we translate one center point onto the other or one circle onto the other. And you would have to count how many units you would have to translate to go from point P to point O. And that would be 12 units to the right. So you could say circle P is translated 12 units to the right. That's one option. Because we talked about that up above, I just kind of want to show a different type of transformation here though, just as an additional example, and it's reflection. So I want to see if I can reflect circle P over the y-axis and make the center points line up. To check to see if that actually happens, you would have to count the distance from each center point to the line of reflection, which is the y-axis. So like point P is 6 units from the line of reflection from the y-axis, and then if I take that point P and I reflect it over, it's going to go from 6 units to the left, and then it's going to go 6 units to the right, and it's going to line up exactly with point O, and the centers will line up perfectly. So we can also talk about in terms of reflection. I'm going to put both of those down, but you really just need one or the other, reflection or translation. So I'm going to say reflection over the y-axis, and then in parentheses I'm just going to say or translate 12 to the right. So one is not more correct than the other. It's just kind of helpful to know both in case you're ever presented with like a multiple choice problem and they only give you one option. So you're able to recognize that both do accomplish making circle P have the same center as circle O. So now I'm going to go ahead and take circle P and I'm going to draw it with the center at circle O. I'm going to erase these lines here showing the reflection. So I just need to check to see what the radius is of circle P, and it's 3 units. So now I'm going to draw a circle around point O that has a radius of 3 units. So have a point right there, right there, right there, and right there. All of those like points are 3 units away from the center. So close enough, I guess. So that new one is going to be what happens when we reflect circle P over the y-axis or when we translate it 12 units to the right. Okay, so now you can see like, okay, so circle or point P lines up with point O. Circle P is just smaller than circle O. So if you just need to change the size now, that's going to be a dilation. So a dilation can make something bigger or smaller without changing the general shape. When you talk about dilation, you need to be able to figure out the scale factor, which is going to come in like how we get one radius to change into the other. So we need to know the radius. So on circle P, the radius is 3. And then on circle O, the bigger circle, the radius is 5 units. So sometimes it's kind of easy to see what the scale factor is. Like for example, if our bigger circle was 6, then we'd be like, oh, well, we just have to multiply 3 by 2 to get to 6. So scale factor would be 2. But we have to figure out how we go, what we need to multiply 3 by to make it equal 5, which isn't, I don't know, that doesn't live rent-free in my brain. So we can set up like a little equation like off to the side to help us find it. So we're going to take the smaller radius, 3, and we have to multiply it by something, but we don't know what that something is, so that'll be x, and we need that to equal the bigger radius, which is 5. So then now we have a little equation that we can solve for x, and then that x is going to end up being our scale factor. So the 3 is being multiplied by x. I need to divide both sides by 3. These cancel out, and then I'm left with x equals 5/3. So that 5/3 is what we have to multiply by 3 to get to 5. So that's going to be our scale factor. So we would say dilate by a factor of 5/3. So first step, reflect or translate, and then second step, dilate by a factor of 5/3. One thing I will say is if you are going from a smaller object to a bigger object, like in this case our circle is getting bigger, your scale factor needs to be more than 1. If you're going down in size, your scale factor should be less than 1, so that should be kind of like a way to check your work. Okay, 15.2, this is arc measures in circles. So arc may be a new vocab word. An arc is a piece of a circle that lies between 2 points on the circle. So on this graphic, there's this arc right here, AB. And then down here in circle C, the path from point A to point B is called arc AB. There's a little bit more shorthand to write that. So you would write it as an A, a B, both capital, and then with a little kind of like arc symbol, I don't know how to describe it, a little like curved line up above it, and that would be read as arc AB, so you don't have to write out the word arc. And then another new vocab is the central angle is the angle that intercepts the arc. So in this picture, it is this little angle inside here is C, and it's kind of like the angle that helps create the arc. So in circle C, the central angle is angle ACB, and again, that's just that little purple one. So the best way to kind of remember what an arc is if you have a like full pizza, like a circular pizza, and then you cut your slice, the crust is the arc. So just the outside curve of your slice of pizza, that's an arc. Okay, and then I'm just going to label those really quick on the right over here. So this is arc AB, and then that little angle inside there is going to be the central angle. So moving down to a couple of rules about arcs and central angles. The measure of an arc is the same as the measure of the central angle that intercepts the arc. So in this picture, you can see the arc is in red, and that has x degrees, and then the central angle is in purple, and that's also x degrees. That's because whatever the size of the central angle is completely dictates the size of the arc and vice versa, so we just measure them the same way. So if like the central angle is 40 degrees, the arc would be 40 degrees and vice versa. And then down here, two arcs in the same circle or in congruent circles are congruent if they have the same measure. Meaning like if I had another arc in this circle over here, let's say I had this angle and then this was my arc, and I said that it was the same degree as arc AB, that would mean that those two arcs are congruent. They're like the same length because they're a part of the same circle, or that's why it says, or if it's on a congruent circle, it's a part of the same size circle, so those arcs would be congruent. Okay, moving down to specific types of arcs. So there's a minor arc, those are like the main ones, and those are arcs that are less than 180 degrees, so less than halfway around the circle. And minor arcs are like kind of like the assumed ones. So for this one, would be arc AB, and you wouldn't have to describe it as anything other than arc AB. Whereas with a major arc, that's not really the assumed one, and you have to describe it a little bit more specifically. So there's a major arc, and that's something that's over 180 degrees, which that just means it's over halfway around the circle. So you can see in this picture, like we could technically describe this as arc AB too, because it has endpoints at A and B. But if I just say arc AB, it's going to assume that it's this one, the small one between A and B. So if I wanted you to know that it was the big one all the way around the circle, you'd have to say major arc AB. Or if there's an additional point, like this one has point D, you can include that. So it would be, you wouldn't have to put major, you would say arc A, D, B. So you'd say arc A, D, B, and because it includes D in it, that shows that it's going that direction, so you do not need to put the word major on it. And then the last specific type of arc is a semicircle. So if an arc is formed by the endpoints of a diameter, it's a semicircle, because the diameter is going to kind of cut the circle perfectly in half. So the two arcs are going to be exactly half of the circle. So there's two in this picture. One is ADB. That would be a semicircle because AB is a diameter. And then the other one is semicircle AEB. And you would just write it as semicircle. So semicircle ADB. It's the first one with the line over it, the curved line, and then the second one is semicircle AEB. Same thing with the line over it. Okay, moving down to the arc addition postulate. So addition postulates, we've talked about a few in the past, and in their most simple terms, it basically says if you take two smaller items and you add them together, you get the total of them both. So like as a review for like a segment addition postulate, let's say I have segment A and then I combine it with segment B, and I call that total one segment C. That means that segment C is just going to be the sum of A plus B because you're combining them together. So that's what addition postulates are. So for this one, it's called the arc addition postulate. So the arc addition postulate, the measure of an arc formed by two adjacent arcs is the sum of the measure of the two arcs. Adjacent just means next to each other. So for this one, let's say I have the measure, which is going to be that little m, is read as measure, arc ABE, which ABE is from here to here to here. So it's kind of like two arcs put together. It's going to be the sum of the two individual arcs. So the first one is arc AB, so we say equals the measure of arc AB. and then plus the other one, which is arc BE. So plus the measure of arc BE. And this comes in handy if you're trying to solve for unknown lengths or unknown arcs within a circle. Okay, moving down, the measure of a circle is 360 degrees. Therefore, the measures of a minor arc and its related major arc have a sum of 360. So a minor arc we know is like something that's less than 180, and the related major arc just means kind of like the reverse of the minor arc. So if the minor arc is AB, the major arc would be AB, but like going the opposite way. So like all the way around here. And because there's 360 degrees in a circle, if we add those two arcs together, we should get 360. And likewise, that means like if you take 360 and you subtract one of the angles or one of the arc measures, then you'll get the other one. So like, for example, you don't need to write this, but like, let's say this is 50 degrees and I didn't know what the major arc was. I could do 360 minus 50, and that would give me 310 degrees for the major arc, because together they have to add up to 360. Okay, moving down to example 1, it says points D, A, and B lie on circle C such that the measure of, this is arc DA, again, I just couldn't really type it, is 34 degrees. You can see that in the picture. And the measure of angle ACB is 51 degrees. That's the central angle for arc AB. We're going to find the following. So we'll find the measure of arc AB. So if we look at AB, it's right here. And early on in this section, we learned that the central angle and the arc measurement are going to be the same. So since the central angle is 51 degrees, that means that the arc measurement has to be 51 degrees as well. Those will always match up. So the measure of arc AB should be 51 degrees. And then the measure of arc DAB, so arc DAB is from here to here to here. And that's using the arc addition postulate, where it just says if we have two smaller arcs, we can add them together to get kind of like their total arc together. So DAB is combining those two smaller arcs. So we would just have to do 34 degrees plus 51 degrees to get arc DAB. So 34 and 51 is 85 degrees. So the measure of arc DAB, again, the two kind of combined ones, is 85 degrees. And then if we want to find the arc or find the measure of arc DBA, notice it's like the same letters. It just kind of like switched the order a bit. So we have to pay attention to what direction we need to go. So we're starting at D, and then the next point we hit is B. So we're going this way. And then after B, we hit A. So it changes the direction. So that's the major arc from like D to A. So we know the minor arc is 34. So to find the major one, we're going to have to do 360 degrees minus 34 degrees, because they're going to add up to 360. So to find what's left, we have to subtract that kind of minor arc from 360. So we'll do 360 degrees minus 34 degrees. And then that ends up being 326 degrees. So arc DBA is 326 degrees. And then I just want to stress really quickly before the end of the notes that you really have to pay attention to the way that the points are kind of, I guess, ordered in the name of the arc. So like the difference between DAB and DBA is like DAB is you're starting at D and then you go to A next and then you go to B last, versus DBA means you start at D and then you go to B second and then you go to A last. So they're completely different arcs and completely different measurements.